Going back to stereochemistry, in the previous classes, we have been learning, first of all, about isomerism. So we learned that isomers are compounds having the same molecular formula. Okay, we define different subdivisions for isomers. So two compounds having the same molecular formula and different connections in between the atoms. Remember, we classified them as constitutional isomers, and I gave you examples of that. However, if we have two compounds with the same molecular formula, same connectivity in between the atoms, and different orientation in space, then we are talking about stereoisomers. That's the definition of a stereoisomer. Two compounds that only differ in the 3D structures, even though they have the same composition, same molecular formula, and the same connections in between the atoms. So in the previous class, we also learned to classify stereoisomers in two different groups. Enantiomers, which are stereoisomers that are not superposable mirror image of each other. This is something we practiced in the last two classes. Non-superposable means that if you put one structure on top of the other one, they don't match 100%. And remember, before arriving to that conclusion, you must be able to flip the molecules either vertical or horizontally and superpose different orientations of the molecules to make sure that they don't superpose, okay? Once again, we practiced this before. And we will do some more problems today. So basically, once you can say that for sure two structures that are the mirror image of one another, they don't superpose, then we can classify these two compounds as enantiomers. It's very important to keep in mind that enantiomers do have the same physical and chemical properties. They only differ in a single property, which is how they rotate the polarized light, the plane polarized light. It's something we will learn more about it in organic chemistry next semester. On the other hand, there are compounds that have the same molecular formula, same connection, different orientation in space, so those are stereoisomers, which are not a mirror image of one another. So basically two compounds that are not a mirror image of one another, but they have the same connectivity and molecular formula, these two can be classified as diastereomers. And diastereomers, in fact, do have different physical and chemical properties. So we said in class also that a better way to classify organic molecules in a more global way could be chirality, and we defined chirality in the previous class too. So a molecule or an object is chiral when it cannot be superposed on its mirror image. So basically, that there are, once again, enantiomers or diastereomers in this group. Okay, I want to say something just as a clarification. There might be diastereomers that are chiral, and we will define that probably later, and you will learn even more about this in organic chemistry, but I'm just saying this now so you're not confused later. But in general, what we can say for sure is that chiral compounds could be enantiomers, could be diastereomers. Okay, there could be diastereomers that are chiral. That's a different thing. And then achiral compounds are those that are superposable with its mirror image. Okay. So how to identify a chiral molecule and what features can you find in a molecule that makes it chiral? So that's the next question that actually you should be thinking about, okay? So chiral molecules are those that are non-superposable with its mirror image. Achiral molecules are opposite. They superpose with their mirror image. So your question should be now, and this is something we discussed in the previous class, what features can you find in a molecule that will make that molecule chiral? How can you identify a molecule and assign chirality, say this molecule is chiral for sure? And the opposite, how can you identify a molecule that is achiral? Or what features could you potentially find in a molecule that will make it achiral? Okay, this is important because that will allow you, once you see a molecule, you can quickly do a classification into chiral and achiral and start thinking about potential stereoisomers. And the way of doing that is by means of something that we also discussed in the previous class called elements of symmetry. Okay, chiral molecules don't have any element of symmetry. That's by definition. Achiral molecules do have at least one element of symmetry. That's basically the way of distinguishing in between them. Finding element of symmetry in molecules. If you don't find an element of symmetry, if a molecule don't have an element of symmetry, then you can say that that molecule is chiral. Therefore, it will have an enantiomer. If you can find at least one element of symmetry in a molecule, then you can for sure say that this molecule will be achiral. If it's a chiral, basically it will be superposable with its mirror image. Basically, it's a chiral, it means that the mirror image is the same compound. Okay? So the element of symmetry that you guys need to be familiar with are two. One of them, plane of symmetry. Definition of a plane of symmetry is an imaginary plane passing through an object dividing it, so one half is the reflection of the other half. First of all, let me clarify that this imaginary plane is defined by 3 points. Okay, I'll go now to another application to show you some examples. So 3 points to define a plane, and the plane dividing a molecule in two sides, one being the reflection of the other side. That's a definition of a plane of symmetry. A molecule with plane of symmetry will be achiral. And then we have center of symmetry, which is a point so situated that identical components of the object will be located on opposite sides and at the same distance from that point along any axis passing through it. Okay, so two elements of symmetry that you need to identify: plane of symmetry and center of symmetry. Plane of symmetry are way more common as compared to center of symmetry. And here is an example. Okay, so here is a molecule. This molecule is basically having, so you see these wedge bonds are coming toward you, the dash bonds are coming away from you. The carbon in the center has 4 bonds, 4 single bonds. That's an sp3 hybridized carbon tetrahedral structure. Okay, that's a tetrahedral here. So you can tell, okay, is this molecule chiral or not? So let's see if we can define a plane of symmetry. So a plane of symmetry is contained by 3 points. Once again, one point will be here, second point will be this atom, third point, 3 points. Each point must be an atom, obviously. Okay, so chlorine is a point, this carbon is a second point, and this hydrogen is a second point. Remember, these bonds, the angle in between here and here is 109.5, and these 2 bonds are going away from you, so this plane is basically perpendicular to your screen. 90 degrees from the screen. So this plane right here is dividing the molecule in two sides, one left side in which we have a methyl group coming toward you, and the right side has also a methyl group coming toward you. So because they are coming both toward you, the plane is right in the center, and because they are the same groups, the left side is clearly a reflection of the right side, so we can classify this as a plane of symmetry. A plane dividing the molecules in two halves, one half being the reflection of the other half. Because there is a plane of symmetry, we can tell, and here is once again the picture is much better, okay? So you see the plane right here, and the points defining the planes are the chlorine, the carbon, and the hydrogen. So this is the 3D picture. You can see the methyl groups going toward you, how one is the reflection of the other side. The molecule is achiral. Here is another example. So here we have, once again, a plane can be defined by these three atoms. And in that case, if we draw a plane right here, the left side is methyl, the right side is ethyl, different groups, so one side will not be the reflection of the other side. And the same thing could apply if we drew a plane over here. So plane over here divides the molecules whose half the top is different from the bottom, so there is no plane of symmetry here whatsoever. And again, these are the two planes of symmetry because each one contains three atoms. Plane is divided by three atoms. Because there is no plane of symmetry or any other element of symmetry, we can say that this molecule is a chiral molecule. Element of symmetry present as the molecule on top, the molecule could be classified as achiral, meaning that the molecule will be superposed with its mirror image. No plane of symmetry as in the molecule in the bottom, the molecule will be chiral, non-superposable with its mirror image. So this molecule in the bottom will have an enantiomer. Okay. I also wanted to show you something here that is very important, and I'm going to already introduce a new concept here. So if you look at the carbon, I'm sorry. I'm trying now, so let me, if you look at the carbon over here on the molecule on the bottom, the central carbon and the carbon over here. Okay, this carbon here is bonded to chlorine, CH3, CH3, I'm sorry. I apologize, so I'm going to repeat this. So the carbon on top, once again, is bonded to a CH, this, I'm focusing on this carbon, is bonding to a CH3 here, a chlorine on top, CH3 on the right, and hydrogen on the bottom. So you can see that this carbon has two groups, CH3 and CH3, that are the same. I don't know why this is happening. I apologize. Okay. So I'm gonna go now to another application to explain this better, because this is not working fine. So this carbon, once again, is bonded to four different groups. Okay, this I can say. So chlorine, CH3, CH3, and hydrogen. The carbon on the bottom here is bonded to chlorine, CH3, CH2. Ethyl is CH2, CH3. I'll draw the molecule now in a different application, and hydrogen. So this carbon here is bonded to 4 different groups. I want to emphasize that, okay? So let me redraw the molecule in a different perspective. So I'm drawing the one molecule here. So you can see how in this picture, okay, this is the 3D picture. So once again, the carbon in the center, this carbon here, is bonded to chlorine, CH3, hydrogen, and CH2, okay? So I'm gonna write it over here. So central carbon is bonded to chlorine, hydrogen, CH3, and CH2. Because this CH2 then is bonded to another CH3. I'm talking about the groups that are directly bonded to the carbon. So you can see how these 4 groups are different. 4 different groups. So a carbon bonded to 4 different groups, we are going to name this carbon as a chiral center. The chiral center is a carbon bonded to 4 different atoms or groups. And I am emphasizing this very important concept. Any carbon, so obviously, because I am talking about a carbon bonded to 4 different groups, a chiral center refers only to an sp3 hybridized carbon, because obviously an sp2 hybridized carbon will only have 3 sigma bonds. The 4 will be pi, okay? So when we talk about chiral centers, we're focusing on sp3 hybridized carbon, and it's an sp3 hybridized carbon with 4 different atoms bonded to it. That's the definition of a chiral center. So one thing that is really important for you is, in addition to finding element of symmetry, I'm going to give you an extra tool to assign chirality, and is the following. If a molecule with only one chiral center will be chiral by definition, because a molecule having only one chiral center, and I'm going to emphasize only one there, if there is more than one, it could be chiral, it could be achiral. Okay, so you cannot draw conclusions. If the molecule only has one chiral center, the molecule can be classified as chiral. You don't even need to look for element of symmetries, because there will be none. Okay? On the other hand, if there is a molecule with no chiral centers, I'm going to say now most, because it's not a general rule. There are a couple of exceptions that we don't cover in this class. But most molecules with no chiral centers will be achiral. Okay? And I'm going to give you an example now. So once again, I'm going to give you an example to compare both. So here we have two molecules. In the molecule on the left here, this carbon is bonded to this carbon is bonded to three hydrogens. Therefore, this is not a chiral center. Three atoms are the same. This carbon here is bonded to two hydrogens. Two atoms being the same, not a chiral center. This carbon here is bonded to three hydrogens. Three groups that are equal, not a chiral center. Now, this carbon here is bonded to four different groups: chlorine, hydrogen, CH3, CH2. So because it has four different groups bonded to it, we call this carbon a chiral center. Okay? And the way to show chiral centers in organic chemistry is by means of using a star symbol. So whenever you look on a textbook and you see a molecule with a star next to a carbon, that means that this is a chiral center. These chiral centers could also be known as asymmetric centers. Okay? So when you look at a molecule and you ask the question, how many chiral centers do you see in this molecule? You need to look at every single carbon. Remember, chiral centers can only be present in sp3 hybridized carbons. And find the carbons that are bonded to four different groups. Those are considered chiral centers, and then you can place star symbol next to it. This molecule here only has one chiral center. Therefore, the molecule could be considered as chiral. Let's look at the molecule on the right side. On the right side, we have a CH3, three hydrogens, no chiral center. Three hydrogens, no chiral center. The carbon in the center is bonded to chlorine, hydrogen, CH3, and CH3 on the left and on the right. Therefore, two groups are the same, CH3 and CH3. So how many chiral centers do we have in this molecule? None, because the three carbons have either three or two similar groups bonded to it. Because there is no chiral center, we can say for now that the molecules that you will see with no chiral centers will always be achiral. As I said, there are exceptions to this, and we will discuss that in organic chemistry, but most of them are not chiral center, are achiral. So then this is a second tool that I'm giving you to assign chirality. So if you want to determine if a molecule is chiral or not, you should look for center of symmetry or chiral centers in the molecule. If there is only one, the molecule will be chiral. If there is none, the molecule will be achiral. Now, if I'm going to write it over here. A molecule with more than one chiral center, so 2 or more, can be chiral or achiral. And in this case, you must be looking for element of symmetry, no matter what. Okay? So that's how I want you guys to assign chirality to molecules in organic chemistry and in chemistry in general. So you look at the structure of the molecule and assign chiral centers. If there is only one, the molecule will be chiral. If there is none, the molecule will be achiral. If there is more than one, then we need to look at the molecule and determine if there is an element of symmetry, and that will make the molecule achiral. If there is no element of symmetry, the molecule will be chiral. Okay? That's important to keep in mind. So here is the once again, the definition, and this is a really important thing because you guys are going to practice this a lot. Okay? So if there is only one, the molecule will be chiral. If there is none, the molecule will be achiral. If there is 2 or more, we don't know. We need to look for element of symmetry to determine whether or not the molecule is chiral or a. Okay, so that's a really important thing. So with those concepts in mind, then I'm gonna give you some examples so you guys can understand this idea of chirality better. So I'm gonna open a new document here. Let's see if you can see it. Okay, no. Okay, let me see. Okay, so here let me give you some examples now. So I'm looking for an application, I'm sorry. So I'm gonna go back here. Here we are. Okay, so let me give you some examples now, okay? So let's look at a molecule like this. So I'm gonna do 2 problems with this molecule. I'm gonna draw this molecule here. And this one over here. And then I'm gonna ask the question, what is the relationship in between these 2 molecules? And when I'm talking about the relationship, let me write the questions here. So what is the relationship and when I'm talking about relationships, we're basically referring to, are they isomers, so constitutional isomers, for example? Are they stereoisomers? In which case we will have to determine if they are enantiomers or diastereomers, or are they the same molecule? Okay, so we need to find out about this. So the one thing that we can do is, first of all, superpose one molecule on top of the other one. So if I try to do this, you can see how they don't superpose. Chlorine in one is going on one side, away from you, and in the one that I'm moving is coming toward me. Okay, so apparently these two molecules are not the same because they don't match. But now, as I said in the previous class, one thing we can do is to flip the molecule over. Okay, so let's see if I can. I'm gonna just look for another application here. And I'm gonna draw here a different molecule. So exactly the one that we had in the picture. And here we have a chlorine atom. Okay, so here is a molecule. Okay, so it took some time. So you can see how this picture here, okay, the chlorine is in green. Okay, chlorine is in green color, going away from you. Okay, the hydrogen is coming toward you. But look at how, so when I flip the molecule over here, so this is exactly the picture that I have, okay? So in this is exactly what I have on the left side. The chlorine is coming toward me, wedge bond, CH3, CH3. Remember, each carbon is sp3 hybridized, 109.5, okay? So in this structure here, the chlorine is coming toward you. And remember, the second structure that I had next to it, it was going away from you. And my question was, are these two molecules, what is the relationship in between these two molecules? When I superposed them, I saw that they didn't match the way I had them drawn on the board, of course, because in one picture, the chlorine was coming toward you. In the second picture, it was coming away. So now, before I draw any conclusion, I need to do a couple of things. Flip the molecule first, because both carbon chains in the picture were following the same pattern, up and down. I don't need to do any vertical flipping, but I can do a horizontal flipping. So if I flip the molecule horizontally, I can see how now the chlorine is going back. Still I have here methyl, and the pattern of the carbon chain is the same. So clearly the relationship in between these two molecules is they are the same molecule. I'm gonna go back to the application and show you now. Okay, here it is. All right, so in the 3D model we have this picture, right? And they don't match like this. However, if we do as we did 2 minutes ago, 180-degree flipping, horizontal flipping, will basically bring the methyl group will be the same. And then now, whenever you flip horizontal, anything that is dashed is going to become wedge and vice versa. Remember, we also went over that before. So it means a flipping, I can then turn my structure into something that it does match. So clearly, these two molecules are the same molecule. Now, another thing that I want to do with this is, So these two are the same. And then my other question is the molecule, because it's just one, it's the same, is it chiral or achiral? And one thing you can do to begin with is to look for chiral centers. How many chiral centers do we have in this molecule? So this carbon has 3 hydrogens, not a chiral center. 3 hydrogens, chiral center, and this carbon is bonded to chlorine, a hydrogen that is going on the back, we don't need to draw it, and then CH3 and CH3, 2 groups that are the same, therefore this molecule has no chiral center. And because it has no chiral center, the molecule will be achiral. Okay? You can also assign that molecule as being achiral by simply looking at element of symmetry in the molecule, okay? So if you draw a plane over here, you can see how this plane divides the molecule in 2 sides. The left is a reflection of the right side. So there is a plane of symmetry. This molecule do have an element of symmetry, which reinforces the idea of the molecule being achiral. Okay, so once again, this is a simple problem, but it basically shows you the skills that I want you guys to really have. Okay, so first of all, relationship in the molecules, you must be able to flip one of them. Remember, to superpose, you want the carbon patterns to follow the same pattern, each carbon chain, okay? This is up and down, then therefore, we don't need to flip vertically. If the carbon chain has opposite pattern, you must do first a vertical flipping to put them into the same pattern. And then the next question is, let's see if they superpose. So this one won't superpose, but then let's do a horizontal flipping, which keeps the pattern the same, but it sends anything that is wedge to dash and vice versa. And by means of the flipping, we can see how these two are the same molecule. If you want to know, or if you need to answer whether or not this molecule is chiral, we have 2 options to answer that question. First, look for chiral centers. There is no chiral center because there is not a single carbon atom here with 4 different groups bonded to it. So no chiral center, the molecule will be achiral. And lastly, you can also look for element of symmetry in the molecule. In this case, a plane of symmetry. And in that case, a plane of symmetry dividing the molecule in 2 sides, the left side being the reflection of the right side. So that reinforces the idea of the molecule being achiral. Okay? So let me give you another problem. So here is another molecule. And I want this molecule to basically answer a question, which is how many chiral centers? And I also want to answer the question, is the molecule chiral or achiral? So chiral centers definition is a carbon bonded to 4 different groups. Okay? So I'm going to show you. So this So it's a carbon that is sp3 hybridized. Okay, sp3 hybridized. So this carbon here has 3 hydrogens, cannot be a chiral center. This one here is bonded to, and I'm gonna just write it over here. This carbon is bonded to a bromine atom, a hydrogen that is going on the back. So we remember we don't need to show, but everybody must know that there is a hydrogen, even though it's not shown in the picture. We understand that there is a hydrogen going on the back there. Okay, so a bromine and a hydrogen. On the left side is a CH3. And on the right side, there is a CH2. So this is clearly a carbon bonded to 4 different groups. Therefore, we can say that this carbon, it is indeed a chiral center. And I'm going to start here, I'm going to place the star symbol to show that it's a chiral center. Next carbon here is sp3 hybridized. This carbon has 2 hydrogens, cannot be a chiral center. This one here also bonded to bromine, hydrogen on the back, which we don't need to show, a CH2 on the left side, and a CH3 on the right side, so 4 different groups. Therefore, this carbon here is also a chiral center. Remember, guys, you cannot find chirality in other carbons like sp2 or sp, okay? Chirality is only found for carbons in sp3 because they are tetrahedral. So in this molecule, we have 2 chiral centers, and then the question of whether or not, so the next question that I had was, is this compound chiral or not? And the answer, as I said before, if there is 2 or more chiral centers, we cannot determine if the molecule is chiral or not unless we look into elements of symmetry. So I'm going to redraw the molecule here and then ask, is there an element of symmetry? And the answer is yes, there is. So right here in the center, if you draw a plane right here in the center, and once again, the plane is defined by 3 atoms, and you might be asking, which are these 3 atoms? Well, is the carbon and the 2 hydrogens right here, okay? So this plane here is dividing the molecule in the left side, which is clearly the reflection of the right side. So they are the same groups on left and right, and one is a reflection of the other side. So here is an example of a molecule in which there is a plane of symmetry. And therefore, even though this molecule is indeed even though this molecule do have 2 chiral centers, because there is an element of symmetry in the molecule, we can say that this molecule is achiral. Okay, so if there is only one center of symmetry, one chiral center, the molecule will be chiral. If there is none, the molecule will be achiral for now. If there is more than one, in this case 2, we need to look at the molecule again and see if we can find an element of symmetry here. And the element of symmetry here is a plane of symmetry. Therefore, because there is a plane of symmetry, the molecule is achiral. Let me give you now another example. So here we have another example of the molecule. In this other molecule, once again, if we look at chirality, we can say, similarly to before, there is a chiral center here, and there is a chiral center over here, okay? No other chiral because there are two hydrogens here, three here, and three here. Two chiral centers, and then I'm asking, is there an element of symmetry here? So there is, I mean, no plane of symmetry over here or over here will divide the molecule in two sides that are the same, but right in the center, if we try to draw the plane of symmetry right here, okay, so what we are looking on the left side is the same as on the right side, except for the orientation of the bromine. This bromine is coming toward you on the left side. The bromine is coming away from the screen on the right side. So clearly, even though the groups are the same in terms of connections, the orientation in the space groups is different. One side is not the reflection of the other side and vice versa. So therefore, no plane of symmetry in this molecule. And because there is no element of symmetry, the molecule will be chiral. So here are two examples. One example of a molecule with two chiral centers having an element of symmetry, making the molecule achiral. A molecule with two chiral centers, no element of symmetry, the molecule will be chiral. And then lastly, I wanted to ask you here the relationship in between, I'm going to call this molecule A, molecule B, and I'm going to draw another molecule here, which I'm going to call it molecule C. And I want to show what is the relationship in between molecules A, B, and C. Okay, so I'm going to look first A and C, these two. Okay, so if I take molecule A and try to superpose this over molecule B, I can tell that they don't match, they don't superpose. However, I'm going to try to flip it before I make any conclusions. Okay, so the carbon pattern is the same in both, up, down, up, down, up, down, up, down. If the carbon pattern is the same, I don't need to do any vertical flipping, okay? So that I know. You can see how the carbon change, they match. However, I can still try a horizontal flipping. If I flip this 180 degrees horizontally to the right side, then the carbon pattern is going to be the same. Anything that is stretched is going to go dash, and therefore we will end up with this molecule, okay? So basically the relationship in between A and C are basically the same molecule. Why? Because just by simply flipping 180 degrees Celsius, 100 degrees horizontally, you can then superpose both of them, same molecule. So because A and C are the same, now let's see the relationship in between A and B. Or C and B, A and C are the same, remember. Okay, so I'm going to draw molecule. So here is molecule B. Here is the other one, A or C, because they are the same, okay? So if I try, so the carbon pattern is the same for the carbon chain. I don't need to do the vertical flipping, okay? If I try to superpose, I see the left bromine matches the right one, it don't match. because one is coming toward, one is going away from you, so they don't superpose. If I flip this, I'm gonna get this molecule over here, and if that's a horizontal flipping, left or right, you get the same. If I try to superpose a flip molecule, once again, now in this case, the right side superpose, the left don't. Right side superpose, the left does not superpose. So it doesn't matter how you flip them, you can see how two, they don't superpose. So you can say now that A and C and B, because they have the same molecular formula, they have same connection in between the atoms, and they don't, and they have different 3D structure, you can classify them as stereoisomers. And then what kind of stereoisomers are them? So the next question then to answer these questions is basically, are they diastereomers or enantiomers? And to answer this question, we just need to know if they are the mirror image of one another. Clearly, they are not the mirror image of one another. So these two molecules will be basically diastereomers. Why? Because they are two stereoisomers that are not the mirror image of one another. They are diastereomers. Therefore, we can tell that they have different physical and chemical properties. Let me show you now another example. So I want to show you another example lastly, okay? Okay, so the molecule on the left is it chiral or achiral? And same question for the molecule on the right side, chiral or achiral. So to assign chirality, you need to look for, remember, you can look for element of symmetry, or maybe you can look into chiral centers. That could give you an idea too. I'm gonna look directly into element of symmetry here. So this molecule here, so if I draw a plane, let's say over here, across these three groups here, so this side on top is totally different this side over here, so that's not a plane of symmetry. But what about if I draw a plane of symmetry like this? Okay, so a plane of symmetry right here is dividing the molecule on the right side and on the left side. They are the same and they are the reflection of one another. So indeed, this is a plane of symmetry in a cyclic molecule. And because there is a plane of symmetry, the molecule is achiral. On the molecule on the right side, the same plane is dividing the molecule in two sides that have the same connection. However, they are not the reflection of one another. In this left side, this methyl group, the CH3, is coming toward me. In the right side, it's at the same position, but it's going away from you, behind the screen. So the left side is not the reflection of the right side, so no plane of symmetry here. And because there is no element of symmetry, we can say the molecule is indeed chiral. Remember, if the molecule is chiral, it means that it does have an enantiomer. If the molecule is achiral, it's superposable with the mirror image. So I'm going to just basically draw the mirror image of both of them here so you can see what I'm saying. So this is this molecule, and then the mirror image will be basically, if we draw a mirror over here, so this methyl group will be on this side, and then this, the reflection of this will be over here. So this is the mirror image, and then you can see how they match perfectly. So this is same molecule. So superposable, same molecule. On the other hand, for this compound here, which we just discussed that it's chiral, it does have an enantiomer. So if we draw the mirror image of this compound, so I'm going to redraw it now. So the mirror image of this compound, this will reflect over here. This will reflect over here. So this will be the mirror image. You try now to superpose, and you see how they don't match. One is away from you. If you flip this to the right side 180 degrees, okay, then this one is going to go dash, this one is going to go wedge. They don't match, okay? So the relationship in between these two, they are enantiomers. Because they are enantiomers, so I'm going to say mirror image of one another, non-superposable enantiomers. Okay? Same physical and chemical properties, okay, for enantiomers, remember. So a summary of what we have discussed in the stereochemistry, again on Thursday, we'll do a review class of the other chapters, but I will include a stereochemistry as well, okay? So a summary of this is that I want you guys from this chapter to know basically isomerism, okay? So I'm gonna try to write it here pretty quickly. So you need to know, identify constitutional isomers, which we discussed in class. You need to know stereoisomers, and this includes basically diastereomers and enantiomers. You need to know chiral and achiral molecules. Basically, when you're looking at a molecule to identify if the molecules are chirals or achirals, and we also learn to assign chiral centers in molecules. sp3 carbon with 4 different groups bonded to it, okay? So these are the things that I think you should know after this chapter. So once again, understanding constitutional isomers, identifying stereoisomers and classifying them as diastereomers and enantiomers, determining if a molecule is chiral or achiral based on either element of symmetry or chiral centers, and then obviously assign chiral center to any molecule. That's basically the goal that I have for this chapter. I'm going to write it over here. And everybody, I will upload problems here on Blackboard later today for you to practice this, okay? So you can look into two molecules, 3 or 4, and determine if they are constitutional isomers, if they are stereoisomers, if they are diastereomers, if they are enantiomers, assigned chiral centers. I'm sorry. Oof. And so forth. Okay. So, and part of doing this correctly is being able of flipping the molecules vertically or horizontally, and then understanding what happens with the carbon chain when you do that. Remember, a vertical flipping inverts the carbon chain, and in addition to that, anything that is wedged will go to dash and vice versa. The horizontal flipping will not change the direction of the carbon chain. However, anything that is wedged will be dash in the flip molecule and vice versa. So you need to be pretty good at flipping molecules to be able to determine if they match or not once you superpose them.